let's start now. Wait to see if this is.
Okay, so welcome to the live stream for the Math1231 and 1241 Semester 2 2017 Class Test 2.
Yes. So as you are aware of now, Class Test 2 is a mix of algebra and calculus, so we're going to be doing a mix of algebra and calculus in this live stream.
Yeah.
Now we're only going to be doing this for an hour, so at the end of the hour I will go and find the old live streams from the last session where we had algebra by itself and calculus by itself, so you'll be able to see an additional hour of algebra and calculus if you want to see it.
Yeah, and we tried to have a different selection of questions from those, so if something's not covered in this stream, then it's probably in one of the other ones.
Yeah.
Okay.
So I think Jonathan's going to start with this problem.
Yeah. Okay. So I think I need a pen. Is this a good one?
Yeah, well, the big blue one.
Big blue one. Okay. So what we have here is a problem. I've slightly abbreviated the wording, but we want to show that something here is a linear map. This function from P2 to R2. This is the space of polynomials of degree 2 or less. And this is just R2, the usual R2 vectors with two real components. We want to show that the map T, which goes from polynomials of degree less than or equal to 2 to R2, is a linear map, and that's T is defined in this way here. So if you have a polynomial, then you evaluate it at 1 and evaluate its derivative at 2 and put those into the two components of the vector. We want to show this is a linear transformation or linear map. Okay, so in order to show it's a linear map, we need to show two things. We need to show that the map preserves addition, and we need to show that it preserves scalar multiplication. So we'll just do those two things separately. Now, I prefer to think of T acting on a polynomial. I probably wouldn't, if I was writing this question, I probably wouldn't put that x in there. I would just say the map acts on a polynomial without saying what the variable name is. And so what do I want to do? So I've got to do two things. So let's first of all do the vector addition one first. So let's let P and Q be elements of P2. So these are polynomials of degree 2 or less. So quadratics, linear things, constants, or possibly 0. And I might also have think ahead and define a scalar. So lambda is a real number. Okay. Now what I want to do is to consider what happens when T acts on the sum of my two polynomials, like so. Okay, so what I need to do is, this tells me that this formula over here tells me what T does. It gives me a vector with two components, and the first component is the sum of these two polynomials evaluated at 1, and the derivative of the sum evaluated at 2. Okay, now what does this actually mean when P and Q are polynomials? I might just write something perhaps down here to say what I mean by that. So P plus Q is the polynomial. P plus Q is the polynomial defined by, this is the way it acts. This is how you evaluate it, I should say. P plus Q evaluated at x is P of x plus Q of x. Okay, so this then is just simplifying in here, this is p of 1 plus q of 1, and this is p dashed of 2 plus q dashed of 2. Okay, and remember what we're hoping for is that this preserves addition. We have to think about where we're going. We want this to be t of p plus t of q. Let's see what we've got so far. So here, this can be split up just using what we know about vector addition. This is just the same as that. And this is, thankfully, how t acts on p, and this is how t acts on q. So t preserves addition, and that's the first property we need. So I'll call this property 1, hence t preserves addition. Just addition. Okay. All right. Well, now we need to do the same for scalar multiplication. Oh, yes.
Question.
Yep.
So if we want to be pedantic, we probably do because it's maths. This step here, do you want to have the derivative of the sum is the sum of the derivatives?
Yes, I just went through that fairly quickly there. Yes, of course. We know that differentiation is itself a linear map. So the derivative of the sum of two functions is the sum of their derivatives. So perhaps I left out a little step. Maybe I'll make a little note of that here. So p plus q dashed is p dashed plus q dashed. That's just the usual rule of differentiation. If you have the two functions and you add them, you can take the derivative of the sum just by differentiating the two separately and adding them up. Okay, now for property 2, we want to do the same kind of thing for scalar multiplication. So let's consider what happens, what t does to a scalar multiple of p. And I guess I need to decode what this means in the same way as I did for that. So let's just say that lambda p is the polynomial. I'm not going off the bottom here, am I? No. The polynomial defined by lambda p of x is equal to lambda p of x. It sounded like I said the same thing there twice. This is the new polynomial obtained by scaling, and the way it works is just you scale its values. Okay, so this means, okay, so the definition of t tells us that this should be lambda p evaluated at 1 and lambda p's derivative evaluated at 2. Okay, so the first one, according to what we know there, is lambda p of 1, and the second one I'm using a rule of differentiation that says that the derivative of a scalar multiple is just that scalar times the derivative. So again, I'm jumping a step here. Josh mightn't be pleased, but there's two steps in there really. First of all, this is lambda times p dashed, and then that's lambda p dashed of 2. Okay, now for vectors we know that if we can take a scalar factor out of all the components at once. So this is lambda p1, lambda times p1 and p dashed at 2, p of 1 and p dashed at 2. And this is lambda times what t does to p. Okay, so that tells us that t preserves scalar multiplication. Scalar mults will do. And the two properties 1 and 2 together tell us that t is a linear map. Or linear, well, the question said linear transformation. Same thing. Okay, how did I do?
Yeah, I think that's very well done. So you do have to, I mean, some of these steps look similar to what you're doing with subspaces before, but this is about two properties, the scalar multiplication property and the addition property. So property 1 and property 2. So make sure you understand how these are different. I mean, they have very similar structures.
Yeah, it's common to see in students working confusion between the terminology when you're showing a subspace and when you're showing something as a linear map. So maybe have a look at two examples of that side by side and just see how they're similar, but they are doing different things. T is a function that takes you from one space to another, and we're trying to show that that has this nice property that it works like this.
So
okay.
Preserves the addition. So those are kind of the key terms if you want to work out the words you want to describe what's going on. Yeah.
Okay.
That's fine.
All right. Shall we move on?
I'll go on with the calculus question.
Something to clean the board.
So this question, you can see where it comes from. I actually haven't abbreviated it very much. This is pretty much as it appeared in the test. And it's sort of not really giving you any hints about how to answer the question. It's just saying, solve this differential equation. And this isn't typically the way we write these differential equations. So, firstly, I might just rewrite this in a more standard way. So I'm going to rewrite this as, I'm actually going to move one term to the other side. So it's the same as the equation. So it's this first order differential equation. And I'm actually going to move one term to the other side, which will be clear in a second why I've done this. So you have this factor times dy dx must equal this. Now, first things first, this is non-linear just because of this y times this and also this square root of y. So any techniques we have for linear first order equations aren't going to work. But if you stare at it, and sort of after your initial panic, you may notice this is just a product of a function of x and a function of y, and this is just a product of a function of x and a function of y. So I can move these factors around and end up with a function of x on one side and a function of y on the other. So I'm going to rewrite this as well, I should say the same as, this is equivalent to the following equation. So y over square root of 4 minus y squared dy dx, and that is going to be equal to minus x over square root 2x squared plus 3. And that's actually something I can fairly easily integrate with respect to x, and this is also something I can easily integrate with respect to x, because I already have the derivative of y sitting there. So I'm actually just going to do this in place. So maybe I shouldn't have said this is the same as much as I should have said this implies. I'm going to integrate this dx, integrate this dx. So I'm just integrating both sides with respect to x. Now the nice thing here is, well, this is really just a dy element, so it's really just an integral with respect to y. So, well, I'm guessing it's something like 4 square root of 4 minus y squared, just because I already have a y here, which I need for the derivative of that. and the derivative of a square root is 1 over that square root. So this is pretty much what I think the answer should be, but it's not quite right. Because when I do take the derivative, so I'm just going to do this, and I would actually do this during the test somewhere on some scrap paper if you have it. If I look at the derivative of my guess for an answer, right, this is this to the power of a half, you get 1/2 4 minus y squared to the minus a half, that's good, I need that for this, times a minus 2y. That's the derivative of the inside. So that's the chain rule. And these twos cancel out. So it's not quite this, it's actually minus this. So I can actually tell you it is that. When you do this integral, you do get this answer. Alright, so that's one integral done. I also need to do this integral, and you can guess it's fairly similar. So I'm guessing it's something like, it has to be something like the square root of 2x cubed plus 3. Now again, I'm going to get a factor of a half, and I'm going to get a 4x. But I actually, I'm going to get a factor of a half and a 4x, which will give me a 2x. I don't want a 2x, I just want a minus x, so I'm going to fix it up by minus a half. So again, you can just take the derivative of this now, and you can show this does work. And there was an integration done, there is a constant of integration. So this is a nice general equation governing this system. And what we'd like to do now is find the solution which corresponds to this initial condition. So for y equals 0 at x, well, I'm going to get minus the square root of 4 minus y squared is equal to minus a, what am I doing? Y was equal to 1. So we get 4 minus 1 is equal to minus a half. X was equal to 0, so that's root 3 plus c. So, well, this is minus root 3. So if I have minus root 3, well, I can tell you that c would have to be also minus a half root 3. Because 2 halves of root 3 make a whole, but they're negative. Anyway, so that is our c value. So I'll just summarize what I found. And personally, this is as far as I would go with this solution. But maybe it's not far enough. So I get that solution implicitly to this equation, this differential equation, is the following. So would you think that's an acceptable solution?
Yeah, I think that's fine. When you have when you solve these differential equations, you often end up with something which is not y equals a function, and here perhaps you could square both sides and get y on its own, and it might be worth doing, but it would look rather complicated and horrible. So maybe stopping here is fine. I don't think you'd be penalised for that. If you can write down a nice simple expression very quickly for y on its own, I think it's sort of polite to do so. But
yes.
Here I think it's fine to stop like that. Yeah.
Okay.
Okay. All right.
Maybe another calculus question?
Yeah. So maybe I'll do that differential equation one there. Okay, so maybe I'm going to use the blue again. Alright, so here we've got a second order linear constant coefficient homogeneous ordinary differential equation. Lots of terms there. And we're asked to find the general solution of this. Okay, so there's a standard method that you use to find this solution, and you can start at different stages. Essentially, the standard method is to make a guess that y is e to say lambda times t, and then see what the consequence of that is. But immediately, you've probably seen this before. You should have seen this before. And if you try y equals e to the lambda t, then a factor of e to the lambda t appears in each of these, which you can cancel out. So you could just jump straight to the equation for lambda without writing this first little bit down, but I might just do it. So first of all, we try y equals e to the lambda t, and this gives the characteristic equation. So when you take the derivative of this once, a lambda comes down, and again another lambda comes down, you get lambda squared. So the second derivative is going to have a lambda squared in front, and I'm going to cancel out all the e to the lambda t's and just write down what we're left with. The second derivative gives you a lambda squared, the first derivative just gives you a lambda, it's 8 lots of the first derivative, and then there's just an e to the lambda t which has been cancelled out here, so this is plus 16. So we're always going to get a quadratic if you've got a second order equation, and so we can now solve this to find the roots. Is that an easy one to factor? So 16, 4 and 4 maybe. Is this?
I usually start with a discriminant as a quick sanity.
But is this lambda plus 4 all squared?
Yes, it is.
Oh, good. Okay, so this has got a repeated root. So I might even write that as lambda equals minus 4 comma minus 4, just to emphasize that it's a repeated root. And in that case, our guess here only gives us one solution, lambda equals e to the minus 4t, but we need two independent ones, and there's a standard method to write down the second one. So I'll say hence two independent solutions. You probably don't need to write this line down. Y1 is e to the minus 4t, and y2 is t times e to the minus 4t. So this is the standard result. When you have a repeated root, you have one solution that you found, and then t times that solution is another solution. If this was a root was repeated triply, if you had perhaps a third order equation, then you would also have t squared times that. Okay, so the general solution is y equals some constant, let's call it capital A, times e to the minus 4t, plus some other constant, maybe b, t, e to the minus 4t. Okay, so that's it. Important things to note here, of course, we've got a second order equation, two arbitrary constants in our equation, that's what we'd expect. Yeah, if this question doesn't have any initial values or boundary values to let us determine A and B, so we just leave it like that. This is the general solution. What do you reckon?
Yep. Should we mention what happens? There are a few questions where you're asked to have a guess at least at a particular solution.
Yeah, so sometimes if there wasn't a zero on the right hand side, you would first of all solve an equation with a zero, and then you'd also be looking to guess or find a particular solution to the equation without something non-zero here. Yeah, and then what do you do?
Well, there are a lot of cases you need to think about. There's especially a case that happens when this thing turns up.
Yeah, well, I think it's basically you need to. It's probably a long thing we don't need to do here, but you would be guessing something of the form like this. There's a table in the notes that tells you what you should guess for each of the different forms you have on the right hand side.
Yes.
Yep. But that's not being done here, so maybe it's just we'll just leave it at that.
Okay.
Do you want to do the probability one next?
Yes. So there's a very wide range of topics to be covered. This includes probability. So we'll try and do one of these probability questions from the algebra class.
Yeah, I picked the easy one, so Josh could do the hard one.
Okay. So this is a very wordy problem. It's even wordier when you look at the original question before I tried to cut it down to just the basics. So the situation we have here is we have two lots of dice. So we have some red die and some red dice. I guess I got the pluralization wrong there. Yeah. So some red dice and some blue dice. So the red dice are very biased. They always tend to show ones instead of anything else. They do occasionally show a 2 and a 3. So the 6 faces have 4 ones, 1, 2, and 1, 3. And you also have these other 3 blue dice, but they're biased in a different way. So one of their faces is 1, 2 of their faces has 2, and 3 of their faces has 3. So these aren't fair dice. Now, the way the question is set up, you're going to pick one of these dice at random, just uniformly at random from the 7 dice. And you want to answer some questions about what happens when you throw this random dice. So we have a few probabilities we want to calculate. First one is, well, let's calculate what happens. Let's calculate the probability that we select a red dice and then throw a 1. So this is in all the universe of all these throws we do, what proportion of them are actually red dice landing on a 1? So I think my preferred method for doing this is to use a tree. There is a nice way to express the situation using a tree. So what we have is, I'm going to let's set up 2 variables. Let R be the event a red dice is selected, and I'm just going to let the value x be the value thrown. So I'm looking for the probability. I might just write down what this is saying. This question is asking me to find the probability that we select the red dice and x turns up a 1. So we can really easily collect together this situation if we were to make a tree. So first things first, in this situation we either select the red dice or we don't select the red dice, which means we select the blue dice. So I'm still going to write this using the set notation. This is the complement of selecting red, which is selecting blue. So according to this, 4 of 7 dices are red. So there's 4/7 chance that we end up heading up this branch. And that leaves us 3/7 chance that we end up heading down this branch. And now we have some conditional probabilities. We can either roll a 1, a 2, or a 3. And when we select the blue dice, we can also have the same thing. We either roll a 1, a 2, and a 3. And just so we understand what's going on, I'm going to work out all these conditional probabilities. So if I've selected a red dice, the chance that I roll a 1, well, these are all going to turn up evenly at random. So I'm going to get 4 out of these 6, or 2/3. So 4 out of 6 turns up 1. Only 1/6 of the time will it turn up a 2, and 1/6 will turn up 3. Now I should point out, this 1/6, for example, this is the probability that x equals 3, given the fact that a red was selected. So there's some notation to remember there. This is a conditional probability. It depends on what dice I chose. Alright, now for the other dice, if you end up choosing a red complement, blue, you end up with 1/6 of the time it turns up a 1, 2/6 of the time, or a third of the time, it turns up 2, and 3/6 of the time it turns up 3, or half. So when you select a dice here, half the time you roll a 3. Alright, so what we need is we want to calculate the probability of r and x equals 1. Now, maybe Johnson can remind me, the notation for this probably shouldn't be n, should it be the that for and? Or is that not really?
Yeah. So
Maybe the word and is clearer.
Yeah, probably I'd write and.
And. So
If you want to use a logic symbol, it's like a.
Yes, yes.
a
So let's just go and. So there's two ways to calculate this, and this is using what we call the law of total probability. So the probability, oh no, sorry, this is actually just a direct calculation. So we have the probability of selecting a red and throwing that dice and rolling a 1. Well, it's the probability that you get a 1 given that you selected a red times the probability that you actually just selected a red. So this is a conditional, this is just a law of multiplication for probability, which really just means you head along this branch and then head along this branch. So firstly, the chance of us selecting a red was 4/7, and when I selected that red, there's 4/6 chance I actually roll a 1. So this is 16 out of 6 times 7, I believe, is, so 6 times 6 is 36, so 40, I got my brain, do it faster. 42, is that?
Answer the ultimate question.
I believe it is. I was just wondering if that was tricking me. So 16 out of 42. And well, I could simplify that, but I think I'm going to leave it as this. So there are, I mean, this is definitely not as simple as can be, but it's good enough. So 16 out of 42 times, when we're doing this, we'll have selected a red and thrown a 1. Now, the next one we want is we would like to work out what the chance is that we actually just throw a 1. So I'm going to erase this. And this is using the law of total probability. There are two ways you can throw a 1. So just the probability that you throw a 1, that's the same as the probability that you select a red and when you roll it, it turns up 1, plus the probability that you don't select the red, but select the blue, and it rolls a 1. So those are the only two ways to do it, and you can't do both at the same time. You can't choose a red and not a red. There's no red blues. So well, we already know the answer to the first question. The probability that you select a red and throw a 1, that was 16 out of 42. Now to work out the second number, well, I want to know what is the chance I select a blue and throw a 1. Well, that's going to be this times the conditional probability. So 3/7 times 1/6. And here's where it's kind of nice that I didn't simplify, because now it's 16 over 2, 42, plus 3 over 42. So the ultimate answer to this question, at least, is 19 over 42. And I think 19 is prime, so that's as simple as it gets. So 1s do turn up fairly frequently. 19 out of 42 is not a small proportion. So the last question we'd like to answer is, well, we want to work out the probability that a red dice was thrown, given that all we know is it was a 1. So in this situation, it's like your friend has rolled the dice, picked it up, looked and said, oh, I rolled a 1, but he didn't tell you what color it was. So you want to get a probability of what color that was. So to do this, we do need to use the, well, I believe it's called Bayes' theorem, but I'm not sure they call it that in this course. So there is a nice way you can work out these conditional probabilities in terms of other probabilities. So for part C, so Bayes' rule tells us we're trying to work out the probability here that the dice was red, given that all we know is that a 1 was rolled. Now the nice way to write this is it is actually just the same as the probability that you roll a red and a 1. So this is just a standard probability, no conditional probability here.
You're using your intersection symbol. Yeah, that's all right.
Yes,
Yeah,
yes,
that's fine.
yes. Sorry. Old habits die hard. So roll a red and we get x, so we roll also a 1 divided by the probability that we just roll a 1. So this is really, if you think about it, it's saying what proportion of the 1 rolls are red. So if you took all the universe where a 1 was rolled and just looked at proportion, all the universes where a 1 was rolled, looked at proportion that were red, you'd have this number. And which is really nice because that's actually the two numbers we did calculate earlier. I might have a word of warning, that won't always be the case. Usually it's intended to be the case, but a typo crept in a previous test, so sometimes you'll have questions that aren't exactly what you're just imagining. So make sure you read the question, make sure you're answering the correct question. But nicely here, I know these two numbers already. So the probability that I roll a red and roll a 1, well, that was the first calculation, 19 over 42. And the probability, no, sorry. That was the first calculation I erased, which...
Is it 16?
well, I can do it here, 6 times, yeah. So 16 out of 42. And the probability that I just roll a 1 in general is given by this number, the 19 out of 42. And when you simplify this, you get 16 out of 19, which is quite high. If your friend rolls a 1, and if your friend rolls a dice, tells you it's 1, it's very likely he rolled a red dice. And that kind of makes sense because these dice are very biased ones. So it's more likely that it will be a red dice in that situation. Any comments about that?
No, I think that's all pretty clear. Then you can use this set notation if you're treating these things as sets. If you know other notation, there's no prohibition on other notation as long as it makes sense.
Well, I did want to avoid that because saying x equal to 1 isn't really a set thing. It's a statement about a value. So I should, I think, be using and. Okay. Right. So which one next?
Yeah, I'll do the matrix one.
Right.
Okay, so here we have a question about matrices with rank, nullity, and image. There are other questions which ask you for things like a basis for some of these spaces that are involved. But this one here just asks you for the rank and the nullity, which are dimensions of some of these spaces, and whether B is in the image. Now, often it's there's sort of links between these different parts. So it might pay to think ahead and think about how you do the whole question, because in this case here we're interested in the nullity of A, which is the dimension of the kernel. You need to know what that is. The kernel is the set of solutions to an equation A times x equals 0. We're asked is B in the image of A. That's like saying, is it possible to find a vector x such that A times x equals B? And so you can see that there's quite a strong link between the types of things we're going to have to be calculating here. So maybe I will got some notes here. Probably best not to make a mistake. Maybe I'll do some calculation that will help us with both of those questions. So maybe I'll just make a note to start with. So that, say this question concerns solutions to AX equals B, and in the case of looking for the nullity, we're looking for when B is 0. In part 2, we're interested in this particular value of B, and also for the rank, we're interested in what's possible, what all the possible b's. So maybe we'll try and solve the augmented, or row reduce the augmented matrix corresponding to this system here. Maybe I'll just say, so for x being, say, x1, x2, x3, and b, b1, b2, b3. Okay. All right, so that has augmented matrix. Let me just write this down. So that's -1, 2, 1, 0. Maybe I'll move it to the left actually, give as much room as possible. -1, 2, 1, 0. And I'm just going to put here B1. I'm thinking I'll maybe use that as 4 later, and I might use it as 0 later. Okay, so I'm going to do some row operations on this so I sort of understand what the solutions are to this. For the rank and the nullity, we're interested in sort of dimensions of spaces related to this system of equations. And for part 2, we're interested to know whether there's a solution that has this particular choice for B. Okay, so let's just, I think it's fairly quick and easy to do some row operations here. Let's just add row 1 to row 2.
I notice your x only has 3 components.
Oh, of course x is, thank you, good point. I'll need that later actually. Of course, if we're multiplying a vector onto this matrix A on the left, we're going to have 5 components running down here, yes. Well spotted. Okay. Okay, so for row 2, I'm going to do row 2 goes to row 2 plus row 1. That's 0, 1, 1, minus 1, 1, b2 plus b1. And for row 3, I'll do row 3 goes to row 3 plus 3 lots of row 1. And then we'll get a 0 here. And I think we get 4, so that's minus 2 plus 6. 1 plus 3 is 4. Minus, is that minus 4? Oh, it is. My notes have it as 4. What was it? I guess it's
It's possible I put it down wrong.
No, I think I copied that one, yeah. Okay, so let's, yeah, it's minus 4. Okay, so minus 4 plus 3 lots of 0, I should be able to do that. And 1 plus 3 is 4. Okay. And then B3 plus 3B1. Okay. Alright. So now to get it into row echelon form, we just want to add or subtract off 4 lots of row 2 from row 3. So row 3 is going to become row 3 minus 4 lots of row 2. And now this actually just cancels out all zeros. And here we've got B3 from row 3 minus 4B2, and we've got 3B1 minus 4B1 is minus B1. Okay. All right. So why were we doing this? Forgotten all about what we were doing this for. We want to find the rank of A and the nullity of A. Okay. So maybe I'll just maybe I'll just do the rank of A first. Okay. So this system of equations is only consistent, of course, when this right-hand side is 0, and for the so if we're interested to find out what possible x's we can have that will give us a b, we need this b to be, this component here to be 0. So that cuts down the possible b's. Okay, the b's are all the things in the image of A, all the things you can get from A times a vector. So so this cuts down. So b lives in a 3-dimensional space. This cuts it down by 1 essentially, doesn't it?
Mm-hmm.
So it's 2-dimensional. There's one condition there. Okay, so for part 1, we can see that the rank of A equals the dimension of the image of A is equal to 2. There's just a 2-dimensional space of b's. We've got one condition on the b's. Yeah, we can specify, if you wanted to specify all the b's or explain, parameterize all of the b's that were allowed, you can pick, you've got to have this equal to 0, and you can pick b1 and b2 however you like, and that would determine b3. So there's only two parameters in there. Okay, so I should say you've got to give a reason, since the image of A is vectors like B. For B in image of A, we need B3 minus 4, B2 minus B1 equals 0. And this is, if you like, this is a plane in 3 dimensions. That'll probably do. Okay, so the and the nullity of A equals the dimension of the kernel of A, and the dimension of the kernel of A is the set of solutions to AX equals 0. So that's when B equals 0. When B equals 0, this is consistent, and we're just interested to know how many parameters we need to introduce to write down the solution. Now there's 2 leading columns here, and 3 non-leading columns. So if we were solving this with B equals 0, we would introduce 3 parameters, and so the solution is 3-dimensional. So there's lots of ways you could write down a reason for that. You could say that with B equals 0, the system is consistent. And there are 3 non-leading columns. Hence, the solutions to AX equals 0 is a 3-dimensional space. That'll do. Okay, so that's part 1. Part 2 is B in the image of A. Okay, so we've basically done all the work we need here. We're just interested to know whether this system of equations is consistent. Can you find an x in the case where B is exactly this vector here? And so the question is really, is this a solution to that being 0? So maybe I'll just write that over here.
We're going to do part 2. Can I make a comment about part 1?
Oh yeah, sure.
So, I mean, this is nice. It shows a very good geometric explanation for what the dimension of the image is. So it is just a plane in R3. There is another reason I would think about giving, just because it does relate to the number of leading columns. So when you're looking at this row reducing, these 2 columns are leading, which really means that these other 3 columns are linearly dependent on those 2. So there is a way to make an argument where you could actually just construct a linearly independent spanning set. So you could actually construct a basis by pulling out
So you're saying
columns.
these two vectors here are the basis, are a basis.
These two
for
columns here, they form you can think of them as vectors which form the basis, and there's two vectors in that basis. So in the end, it really just comes down to counting the number of independent columns. So that's another way to do it, to sort of think about the linear independence this implies.
Yeah, actually, I have another way too. If I've already worked out the rank is 2, or if I worked out the kernel is 3, then I could get the other one from the rank nullity theorem, which says that these two things must add up to 5, which is the length of that vector there, the vector we're mapping from. So the rank nullity theorem says that 5 should be the sum of these two things. So if you've got one, you can just quote the rank nullity theorem and say what the other one is. Yeah. Okay, so part 2 we want to know is B in the image. In other words, does the B we're given essentially lie in that plane where that's equal to 0? So so I guess I just want to check, let's just maybe B is in the image if, I'll take of A if B3 minus 4 B2 minus B1 equals 0. Let's just check that. Since there's B1, no, there's B3, 8, minus 4 times B2, which is 1, minus B1, which is 4. I'm hoping this is 0, is it? 8 minus 4 minus 4, good. Since that equals 0, let's just say 4, 1, 8 is in the image of A. It's an element of the image of A, that'll do. Okay, so that's I think the answer. Now, I thought ahead and did this working once. It's quite common to see student answers where they do some working for this, which would be exactly this with zeros down here. Then go, okay, now I'm going to do the same thing for B, do all the row operations again. There's nothing wrong with that. It's just apart from the fact that it's just a bit inefficient, and you'll, if you love doing row operations, just do more and more of them. But maybe this way we can get away with a bit less working.
Yeah. That's good. There's maximum information recovery, I guess, from making this choice.
Yes.
So you end up with very general conditions you can exploit at the end. So, because when you're considering the kernel, you're thinking about zeros here. But if you're considering this particular question, you want to have another. You want to have the power to go change your question.
Yeah.
Okay.
Let's see. We've got time for another one?
There's 5 more minutes. I think I might be able to say enough about this last one.
I reckon give it a go.
So this is another differential equation. We solved one earlier which was separable and had an initial condition. This one doesn't have an initial condition, which is nice because we have less work to do in some sense. And we've also been told it's an exact equation. So we probably should ask ourselves what that means, or remind ourselves what it means for this differential equation to be exact. And again, it's written in a very non-standard way. So I might just modify this on the board and rewrite it as following. So it is this term plus this term times dy dx is equal to 0. This is the differential equation we wish to solve. So just a quick reminder. So we want to show this equation is of the form, well, it's really just, I want to show it's really just an equation of the form, the derivative of some function of x and y, but of course y is a function of x itself. I'll show it's that equal to 0, saying that this thing is really a constant. So what we're trying to show, if I expand this, so we will need to use chain rule to do this, and partial derivatives. So the chain rule says that this is really the partial derivative. So ignore the y, take the derivative with respect to x, a partial derivative. plus the partial derivative of h with respect to y times by the full derivative dy dx. And that's the question. The question is saying, is this equation really of this form? It says it is, but we need to show that. So just some quick notation. I'm going to call this f of xy. Oops. And call this term g of xy. So I want to. The trick for actually showing this does work is to check the cross partial derivatives. So let's start the question. Right, so looking at what we need to match up, I need to let f be equal to this term here. Now it's important you don't try and modify what you've been given. I did see on the forum someone tried to modify the equation then do this check. It only works if they're telling you it's exact, it must be the way it's written. So I'm going to let f of x equal that term, and the term I see next to dy dx, which is this, that'll be my g.
Is that y missing?
Yes, it is. Thank you. Yeah, otherwise my check would fail, and I would have to go back to the drawing board, whiteboard. Right. So yes, make sure we don't make any mistakes copying it down, or we will have an unpleasant time. So I have this f and this g. Now, what I would like to check is that the partial derivative in the y direction of this is equal to the partial derivative in the x direction of this. So, and consider, and I'm very lazy, so I'm going to say I'm trying to check that the partial derivative of f in the y direction, and I'm looking at how that differs from g in the x direction, the partial derivatives that is, just because if this difference is 0, they're equal. I can do all the calculations in one. Okay, so partial derivative of this with respect to y. That's lovely actually, it's just x plus 1 e to the x. And I want the partial derivative of this with respect to x. Well, this thing doesn't even depend on x, so it's going to vanish, and I'm only going to get this term. So partial derivative of this is, I'm taking off e to the x plus x e to the x using the product rule, which is the same as that term. It's just x plus 1 e to the x. So it is equal to 0. That's had to happen. So it was exact. We were promised it exact. If I haven't made any mistakes, this was going to work.
So you've shown that it's exact here, yes.
Yeah.
I mean, you could do this by working this one out, and just noting that they are the same. But yeah, okay, so it is exact.
And let's just make a note of that. So what we've done here does show it is exact, because this difference between these two is 0. Okay, I know it's exact, so I know it is of this form. So what I need to do now is work out what the original h is. So what do we have? So we have, well, we know it's exact now, so I know that there's a h such that dh dx is equal to this term. And I know there is a h such that the y derivative is equal to this term. So I need to integrate one of these to get a bit more information. And contrary to what I would probably usually do, I'm going to integrate this one first. It doesn't look nice, but it's not so bad. So I'm going to call this equation 1, equation 2. So I'm just going to say from 2, we get, well, if you're ignoring x, just trying to think of what would give you this as a derivative of y, you need to integrate this with respect to y, or just note that it really is just going to be this times y, because I'm not really considering x as changing. This one, well, unfortunately it's integration by parts. That's how I would do this. Or, well, I'm confident enough that I can actually write down the correct answer without doing integration by parts, because I can see what I need to cancel out. And if I check this, this does work. So if I take the derivative of this, I will get the term I want by deriving by the product rule, and I'll also get a 2y e to the y. That will cancel with this, and that will cancel with the next. It does actually work, and I know because I've done this before. So you should do integration by parts if you're not sure, but this is the correct answer. And there's one more thing. Because I wasn't thinking about x varying, there's actually room for a function of x. So there's a room for a whole function of x here. Now the way I like to progress with this, some people like to integrate both and try and do a sort of comparison. I don't find myself particularly successful at that. So what I'm going to do is instead take the derivative of this, the partial derivative in the x direction, and compare it to this. So taking the h, the x gives, so if I take the derivative of this in the x direction, I'm going to get the h dx is equal to, well, if you take the derivative of this term, it does just turn into this.
Yeah, that's the product rule, isn't it? So it's
Yeah,
one times this plus x times that.
Yeah.
Is that it?
So this is product rule, but I just collected it together because I can see what's happening. This is all y, doesn't matter.
It's zero. It's got a zero derivative. Yeah.
Yeah. So it's got a zero derivative in the x with respect to x, and then we have the derivative of this. And if you compare that to the 1, we end up with this must be a constant, because this must have derivative 0. So the f prime must be 0. So comparing to 1, equation 1, we see that f prime of x equals 0, i.e. f of x is strictly a constant. So the final answer, implicitly we have the solution that the relationship between x and y is given by, where is it? There. It's given by x e to the x y plus this mess, which can be written as y squared minus 2y plus 2e to the y, equals a constant. I'm just going to call this
Capital
B.
Oh, B. B's good. Yep.
B is a constant.
Okay, so remember this came from the fact that we originally showed that the equation could be written as the derivative with respect to x, the total derivative with respect to x of h was 0. So that's saying that that this thing here is in fact just a constant. So once we found h, the solution is that equals a constant. Of course, solutions to differential equations you might want, really you're thinking of y as a function of x, but it's impossible to rearrange this to get y on its own here. So,
oh yeah, it is possible.
Yeah,
I was about to say it's possible because it was possible because it's a quadratic, but I hadn't noticed
e to the y
Yeah.
mixed in here is going to make it horrendous.
So often you can't do better than this.
Yeah. So we consider this algebraic equation that relates x and y to define y implicitly as a function of x is what we call a solution in this case.
Alright, so that's all the problems we were going to do for this live stream, and now we have to run off. But I will, a little bit later today, find the live streams from previous sessions and previous years and put them up on
Moodle.
I'll put them up on Moodle.
Yeah.
So,
or maybe Ed too, why not?
Yeah, we'll see.
Somewhere, you'll find them.
You'll find them. Right, so
Okay.
good luck.